students opting for especially the space physics paper, but others are also welcome actually. কিন্তু এইটো ক্লাছ টাইম হোৱাৰ কাৰণে ছাৰ আমি কেইজনমান ষ্টুডেণ্টেই পাম, ৰিচাৰ্চ স্কলাৰ আছে, আমি খালি ইউটিউব এক্সেছ কৰিব পাৰিব আপোনাৰ ক্লাছবিলাক।
Okay, okay,
হয়,
okay.
অ'কে।
It won't be much. Whatever is already available, that will I will again or tell him. Okay. So let me begin little bit of introduction on the last hour or so here. We have got some idea about what the ionosphere is and what type of research, etc., is going on. But because this is a course and we are brief I do and okay. In the on Monday, was kind of thinking about something which is not visible studying magnetic fields from 1700 or even earlier than that of the Earth. And we all know that Carl Friedrich Gauss was a very good scientific mind in terms of many of the rules and this magnetic concerning magnetic fields we still owe to him. And he thought that from his observations of these changes in magnetic field near the Earth's surface, basically from magnetometer measurements, he thought that there may be two magnetic fields, one internal within the Earth and another external above the Earth. Okay, so that was in 1839, long back. Then Balfour Stewart in 1882, he first inferred that there may be a conducting layer of conducting region in the upper atmosphere, which may be able to, or which is influencing the magnetic field variations on the Earth. Okay, so applying the vast data accumulated over the period, Schuster, 1889, he demonstrated conclusively that electric currents must be flowing overhead. He demonstrated it. By using experiments, he showed that electric currents must be flowing overhead. Overhead means above the Earth's surface. So this geomagnetic history was not known widely outside the field of geomagneticians. So when Marconi transmitted radio across the Atlantic, as we have said, in 1901, an overhead conducting layer was invoked again by Kennelly 1902 and Heaviside 1902 independently to explain that. So when Marconi came up with that revolutionary experiment, people were trying to explain, and already it was in that in the domain of knowledge that there may be something which is above the Earth's atmosphere. So Kennelly 1902 and separately at the same time Heaviside also, they thought and they predicted that there should be an overhead conducting layer. Conducting layer means which allows the radio waves to propagate, because radio waves cannot propagate through normal atmosphere, normal neutral atoms and gases. So it needs a conducting layer for reflection or refraction. Even though it can propagate directly in free space, but for reflection and refraction, it must have a kind of a mirror. So what is that mirror? That mirror is your conducting layer. And because the Earth is curved, the mirror will also be curved. You have a kind of a concave mirror. A concave mirror over the surface of the Earth, conducting, and which will allow the radio wave to travel to that mirror, hit it, and come back. So that was Kennelly and Heaviside's inference. Then came because and they thought that it should be around 80 kilometers of altitude, at an altitude of about 80 kilometers. And because they came up with this first, so that layer was termed as Kennelly Heaviside layer. Kennelly Heaviside layer. So direct evidence of the existence of Kennelly Heaviside layer was obtained by comparing the fading characteristics of signals received on two types of directional antennas called the E layer by Appleton, Sir Edward Appleton. He was also a Nobel laureate. So in 1925, they came up with this idea or experimental evidence by looking at two signals received in two directional antennas, and they thought that this should be a layer of conducting layer, as Kennelly and Heaviside had predicted, that it should be a layer of conducting layer, and let us call it an E layer. Why E? Because they thought that there may be some other layers also below E, so you may have A, B, C, D kind of. So they thought that let us put a middle kind of a letter here, so that if there are layers above, then you can go F, N, Z, etc. And if there are layers below, then you can have that C, D, etc. So that was the idea, that why it was called the E layer. Now, when this was theorized, because Appleton Barnett, they saw it from the experiments, and then they theorized. They thought that it should be possible, and there should be an E layer. Now, how to get it experimentally proved? Braid and Tube. These two people in 1925 and 1925, they published their papers in 1925-26. Maybe they were experimenting much before that, but we do not know. What they did, they sent radio pulses, short bursts of radio pulses to the, means above, vertically, and waited and found that these radio pulses come back after a lapse of few milliseconds or microseconds. So you have two receiver and transmitter set one receiver and antenna, a set of experiment. You can have one transmitter and one receiver close by and send a signal. Those of you who are conversant with electronics, you know the radio wave pulses. You can have the pulse going up and zero kind of thing. So when the pulse is sent, it is one, and then during that period between two pulses, it can be allowed that the receiver can be allowed to remain on. So you can have switch on and on kind of business. Switch on the transmitter for the pulse going out and switch on the receiver for the duration between two pulses. So by doing that, they found that these pulses come back from somewhere above the Earth's surface. Okay, and by knowing that time difference, they could also calculate the height of the atmosphere, or now we know the ionosphere, from where the pulses came back. Okay. Now, when it came back, how did they calculate? Because this is only a radio wave or an electromagnetic wave. So we know the speed of the electromagnetic wave. So the height, the time taken by the pulse to go to the ionosphere and come back, go to the atmosphere and come back, divided by 2, because it is 2 times. It goes forward and comes backward. So divided by 2, the time lapse divided by 2 gives you the height, multiplied by your velocity, gives you the height of the atmosphere from where it has come back. Okay, so this is 1925, 1926, and that is the first experiment of radio sounding, and that is the forerunner of all modern ionosons. The ionoson which we have in our laboratory is also working on the same principle. You send a pulse, wait for the pulse to come back, and during that period, switch off the transmitter, switch on the receiver, receive the pulse, and then calculate the height, and you use your appropriate equations and all. You can get it displayed on your computer or any other display device, CRT, etc. And then you can reduce the height, reduce the time to height from where it has come back. Okay. So let me go to the next slide, because it has started 1925-26. This period actually was from 1901, or say beginning of this 20th century. There were so many developments. Then came in 1918-19 that First World War. So war is always business, plus it also requires communication. So whoever has better communication will survive, or survive means will dominate. So that was the reason why people started working on these kind of things. Plus, of course, the scientific point is scientific curiosity was always there. So a lot of people started working on this, and then finally, what people gathered is you get a kind of a layered structure. You kind of a layered structure in the atmosphere. So many layers. If you can see from here, it is the D layer, then E, F1, and F2. Okay. So here in this figure, this is a picture taken from, or figure taken from some book, mostly Hargreaves. So you see the F2 layer peak, this one. It is about 300 or 350 kilometer, between 250 kilometer to 400 kilometer. And of course, this varies. This varies from location to location, means from latitudes to latitudes. From in low latitudes, the height is more. F maximum height is more compared to mid latitudes or even high latitudes. High latitudes, the height is much less. Okay, again, your layers. These layers do not exist all throughout. Means if you have a 24-hour observation, then your layers will disappear after sunset, or just not exactly just after sunset. There will be some kind of a recombination process still going on, and then around late evening, midnight till morning hours, what you will get is only two layers. Instead of D, E, and F, you will get only E and F. So here, what we have four profiles. You see, we have four profiles. This is for day, this is for night. The black line for day, the dash line is for night. And here, this E and F, as you can see, of course, here F is not divided into F1 and F2 because, as we have shown, this is for sunspot maximum. This is for sunspot maximum, the right-hand side, and the left-hand side, two profiles are for sunspot minimum. Now you know about sunspots. Higher sunspot numbers is and maximum number of sunspots you get every 5.5 hours or 6 years. And similarly, you get a minimum also 5.5 years kind of thing. So 11-year cycle, you know that. And that gives you two types of profiles. This, if you ask me what is a profile, we have been talking about what is means these atmospheric profiles or ionospheric profiles. If some of you are familiar with the experiments which we conducted with the balloons, you have seen that balloons in our laboratory, just in front of physics and CAS, that in the balloon, what you do, you put a number of instruments which measures the meteorological parameters. In our case, it was temperature and then wind and then those kind of things. Okay, so here, if you suppose sit on a rocket, suppose you sit on a rocket and start measuring the density. You can have a density measurement with different type of instruments. There are Langley probes and other things which maybe we will mention after a few classes, how the ionospheric parameters are measured. So you can just hang one solid metallic ball or say metallic tube, solid metallic tube with plus and minus, means positive and negative ends, and connect it to your electrometer, so that you get how much of voltage is getting by the how much of voltage is you have that cylinder or that ball contains at a particular point of time. So that way, these measurements were done. These measurements, because your experiments that Ionosphere also gives you the layers E and F1 or F2 on E or F. We have in our laboratory itself, there are very good ionograms where, if you are interested, go and ask your sir or any of the students who are familiar with this, that you can see from the ionogram itself E layers, F1 layer, F2 layers, but not D. D is not visible. D is not visible to the ionosphere. It can be measured by rockets or say very high altitude balloons, but mostly rockets. D region, we will come to that afterwards. The D region ion density or ions are different from E and F region ions or molecules. So D region mostly it is, the process is also different, and you have mostly negative ions in the metallic ions, negative ions in the D region, which vanishes at night. The amount of ionization is very small, as you can see from here itself in this graph. That amount of ionization is only about 10 to the power 3 in the D region. 10 to the power 3 means 1,000 electrons per centimeter cube. 1,000 electrons in a volume of 1 centimeter cube. So here it for a E region it increases to 10 to the power 5. That means 2 orders of magnitude. In the F region it still goes further, maybe 10 to the power 6 or sometimes maybe 10 to the power 7 also. So per centimeter cube, if you calculate it in terms of meter cube, then multiply this add 6 to this. So it will be 10 to the power 11 or 10 to the power 12 kind of thing. So this is how you get the electron density. Electron density, and as I will tell you again that maybe sometime later, that the ionosphere, it is a ionized medium. It is an ionized medium, and it is supposed to be quasi-neutral. Those who have studied plasma physics already, you know what is quasi-neutral. Quasi-neutral is that Ni, number of ions, approximately equal to the number of electrons. So at any given time, the ionosphere should have equal number of ions and electrons. Okay, so it is supposed to be quasi-neutral as a whole, not in parts. Maybe in some point it is the electrons are higher than the amount of ions and all that. But what you consider as a whole, the ionosphere is neutral, quasi-neutral, not perfectly neutral, but quasi-neutral. That term you already know in plasma physics. Okay, so composition means how the ionosphere density varies. You have in normal atmosphere, from the ground above, you have nitrogen and oxygen. These are heavy molecules. Nitrogen and oxygen are the heaviest of molecules. So they reside near the Earth's surface up to a height of, say, 100 kilometers or a little more than that, equally mixed. Then you have N. N means nitrogen dissociated to N and N. Similarly, O2 dissociated to O and O. And also, by combination, you have NO also. So at lower heights means lower ionospheric heights, already you will have O and N. Instead of N2 and O2, you may also have N and NO and this O. So what happens? So here it is written here. So major F region ion is O plus. O plus is the major ion. Major species if you measure the amount of means if you can distinguish the ions in the atmosphere, in the ionosphere. So around the F region, you will find O plus is maximum. Then will come H plus, then Hc plus, NO plus, etc., etc. That I think we may have some, I don't know whether somebody has got it. During the SROS satellite, SROS, a series of satellites which were flown over India or over the world, you can say, in polar orbits, and ion density was measured with a retarding potential analyzer. So that gave you ion densities, and also you can distinguish the number of ions, O plus and H plus, He plus. We did it here. We analyzed this here. Some of your senior students here analyzed the source data. So you can see what is the percentage of O plus with respect to the percentage of other ions at any height. So here you can see from this graph, O plus starts from about 120 or so kilometer, then it goes to maximum around 250 for this curve particularly, and then reduces up to and goes to the minimum 10 to the power 3 or less than 10 to the power 3 at a height of, say, more than 1,000 kilometers. But O2 plus, you can see this O2 plus is somewhere here. It is maximum here around below 150 kilometer, and then reduces very fast, and you won't get much more O2 above 250 kilometer or so, okay? Similarly, NO plus is like this, maximum around 150 kilometers. That means just above the E layer, you will get a maximum for NO plus, and then it reduces similar to this. Then you have other profiles for N2 plus, N plus. Then you see we have H plus starting from about 400 kilometers. You see, this is H plus starting from, because hydrogen is the lightest atom. Hydrogen is the lightest atom. It remains in the upper atmosphere, not below. So as and when these lighter atoms, O, NO, they give way to hydrogen, it will be a height of, say, 400, 500, 600 kilometers. Beyond that only you will get hydrogen ions, because hydrogen should be there for ionization. So you will get hydrogen ions above about 400 kilometers or so. Okay. Now, neutral gas concentration at 300 kilometers is 10 to the power 8 per centimeter cube. This is the picture below. You can see from here density of O, N2, and O2. O is that red solid line, N2 dash line, and dot line is O2. So density decreases. Density decreases from, say, lower height, 80 kilometers or so, maybe 60 kilometers. Density decreases from 10 to the power 16 per meter cube to 10 to the power 14 per meter cube at a height of 300 kilometers or so. Okay, so 10 to the power 14 means 8 in centimeter cube. 10 to the power 8 centimeter cube, 10 to the power 8 per centimeter cube, total number of neutrals. Okay, total number of neutrals you will get around 10 to the power 8 at about 300 kilometers. So your ions or electrons, total ion density or electron density will be 2 times less. So it will be 10 to the power 6. 10 to the power 6 per centimeter cube. So 2 orders of magnitude smaller or lesser. So negative ions are found only in the D region. Already I have talked about, and also I have talked about the net charge of the ionosphere is 0. Net charge means the ionosphere, if you have a kind of a measuring instrument which measures the total current of the ionosphere, it is charge, positive or negative, it is 0. It is 0, as we have said. We will consider the amount of negative charge equal to the amount of positive charge. Okay, so this is the concentration. You can see this is O plus. This y-axis is from 200 kilometer to about 1600 kilometer, and concentration per centimeter cube, 10 to the power 3, 4, 5, 6. You get a maximum around 300 kilometer, O plus, and then it reduces, and H plus starts around 500 kilometer. Then go H plus density is more or less, it remains same because to higher altitudes or at higher altitudes, it is only H and some helium. Therefore, H plus density more or less remains same. It doesn't get reduced like what happens for O or NO or other species. And this NE is the total, O plus, H plus. Earlier also we have shown that NE curve, this is the E. This curve is E. E is the total of all the positive ions or all the negative ions. Okay, E plus or E minus. So this is your curve. This is E. E. Okay. So next, the concentration, as we have said, this is here you see O is equal to O plus concentration is equal to H plus concentration here. If my pointer is visible to all of you, this is the point where, or height where O plus concentration becomes equal to H plus concentration, and this is also known as the transition height. Transition means O plus gives way to H plus, and H plus and above we call it plasma sphere. Instead of ionosphere, we call that plasma sphere because that H plus is mostly dominant ion and not plasma sphere, photonosphere. So photons, okay. And here again for some other profile, these are profiles taken by incoherent scatter radar because these are continuous. Radars can take continuous profiles like balloons, but balloons cannot go up. Rockets can go up. So similarly, this kind of profiles, HC, this is helium, this is H, this is O plus, like that. Okay. Now at low latitudes, what happens? Now you know about the plasma. So plasma sphere and the ionosphere plasma sphere interactions, all those things you are now aware of. So from low latitudes to high latitudes, you have these field lines. The field lines start at the North Pole, like any dipole, any magnet you use in the laboratory. Two poles, north and south, and these two poles, north and south, produces an magnetic field which starts from the North Pole and ends at the South Pole. So you have a flux of magnetic field lines, or kind of what you can see, the magnetic field lines. You draw. I think in higher secondary classes or even in schools nowadays, people start drawing these magnetic field lines. You can draw magnetic field lines. So those field lines means the sphere of influence, of that magnet, how it proceeds. So over the equator, the magnetic field lines are almost parallel. Almost, not exactly, but almost parallel. And then you have these field lines slowly dipping towards the Earth's surface. So you have that is given by the dip angle. You know, dip angle, you can measure. You have instruments for measuring dip. A needle which can move in the vertical direction, not in the horizontal direction. Horizontal direction is the compass. Vertical direction is that dip angle you can measure. So if you have this dip angle instrument, measuring instrument you have over the equator, it will be just horizontal. It should be nearly horizontal. Then as you go up, this deep angle, that north will be tilting towards the surface, and then as you go on at 90 degree or around 90 degree around the pole, it should be completely vertical. So here in Dibrugarh, your deep angle is about 43 degree. 43 degree, okay? So it is tilted by 43 degree. Any deep this compass will be tilted by an angle of 43 degree over this location. So now I think I will present in a PDF format the other part of my talk, okay? So now coming down to exactly what happens. We have mentioned about continuity equation. Now all of you know what a continuity equation is, and for number, it is if the number is n and the time is t, then dn dt is production minus loss at any given time for any species, not only for ionosphere, for any other physical process where production and loss is the mechanism, or where production loss mechanisms are there. That means when the continuous production and loss mechanism is there, that means continuous production is there, continuous loss is there, your rate of the species present with respect to time will be that production minus loss, okay? Now in this particular case, dn dt represents the rate of change of electron density, okay? N, capital N, normally you will see in other books also, in literature also, that electron density is normally denoted by N, maybe sometimes a lowercase n or sometimes a uppercase n, okay? Now, this loss term, I had mentioned that, and maybe you know or you are familiar, that this loss term is not only a simple loss. It is not only a simple loss. It has two types of components. One, you have loss due to the chemical reaction between the species. Once O plus and E is created, say you break one O, atomic O, to O plus and E by your solar ionizing radiation, extreme ultraviolet at the particular frequency for ionization of O will ionize. If it is sufficiently strong, it will ionize, means it will separate O to O plus and E, okay? Now that O plus and E, it is free to move. So it may combine with the same E, the same O plus, or it may combine with another E or another O plus, or if other electrons or ions are present, it may combine with an H, okay, or NO plus, like that. So photochemical reactions or photochemical loss means in this case conversion to the atomic state or molecular state. That is not loss as a whole, but loss of ions or electrons, loss of the plasma, not the neutrals, but what you do in the, because of the solar ionizing radiations or the ionizing process, we get to dissociate the atoms and molecules, neutral atoms and molecules to ions and electrons. These are very basic, okay? But when they recombine, so that is a loss for those ions and electrons. For that amount of ions and electrons, if 10% is again recombining, then only 90% will remain as plasma, means and electrons. It is like that. So photochemical loss. But with that, you will also have this transport. Transport means, suppose you just consider a box. You consider a box in your laboratory where you are producing ions and electrons. Okay? So as long as this box is immune to any movement to and from outside, that means plasma not going away from the box, it is a shielded box. So the plasma which you created by ionizing radiations in O or O2 or N2 medium, then these ions or electrons, whatever is generated, will remain same. They will recombine, so you will have only production minus loss, these two terms, production minus photochemical loss. But if you allow transport from the box which you had originally, that means if the walls of the box are transparent, means transparent for the ions and electrons to move away or move in, move out or move in, then what will happen? The number of ions and electrons at any given time may be less if goes away, if some of the electrons or ions goes away, or maybe more compared to what it was at that particular point of time if ions and electrons from other sphere or from outside the box comes in. So that is transport. Now, in the ionosphere and in the lower atmosphere also, you know, winds are there. So in the ionosphere also, winds and other mechanisms are possible. And so transport is always there. Transport is a process which takes place continuously at any point of the ionosphere at any given time. You cannot have a transportless environment. You have a production mechanism, you have a photochemical loss mechanism, similarly a transport mechanism. And the transport can be because of that electromagnetic drift, we know now, because you have electric field and magnetic field. So if in electric and magnetic fields are at cross purposes, that means E cross B, then you will get drifts, okay, perpendicular drifts. Then winds, neutral winds. Neutral wind means the winds which carries the neutrals, these molecules or atoms. The neutral molecules, they carry the neutral molecules. There are wind systems over the Earth at different heights. Sorry, at different heights, and you can see at thermospheric heights also, because this ionosphere is also known as thermosphere in terms of temperature. You know, thermosphere means it is hot. So thermosphere. So at thermospheric heights also you have winds and then diffusion. Diffuse means certain ions and electrons, a group of ions and electrons converge and then diffuse. Then diffuse due to different processes, maybe gravity, etc. etc. So what you get is this. dN dt is equal to Q minus L minus divergence and V, divergence and V. And V is the flux of ionization moving across unit area per unit time due to transport. Moving across means either in or out, okay? So we will discuss the theory of production of ionosphere by photoionization, okay? So after all the activity of this Breit and Tuve conclusively proving in 1925-26 that there is a ionized layer above the Earth's surface, and Chapman and also they theorized that there should be a layer of ionization. So how that ionization will take place and how much of ionization at what height will be possible. So he tried to have an equation or try to derive an equation for production of ionization. Okay, so this Chapman's theory, 1931. Around this period only, 1932, he gave that theory, 1931, 1925, 26. Within a period of say 5-6 years or so much of activity. Okay, so Chapman theory dating back to 1931, it starts with a few simplifying assumptions. Because at that time, it was just theory. Nobody knew exactly what is there. So because it was only the ground measurements. At that time, rockets were not that strong to go to ionospheric heights. Second World War has not come. So rockets could fly only up to a very limited height, say maybe 40-50 kilometers or so. That kind of technology was there. So whatever information was possible was from the ionosomes. And ionosomes give you E, F1 and F2, okay? Or maybe E and F, F1 and F2, because those ionosomes were also primitive compared to what we have now, or say 30 years after that, or 40 years after that. So your assumptions, Chapman's assumptions were based on certain, or theory was based on certain assumptions. What did he assume? First was an exponential atmosphere with a single component and of constant height. He assumed that the ionosphere is exponential. In this case, we have written atmosphere, but it is basically what concerns the ionosphere or ionization. So that atmosphere is exponential. Exponential means exponentially varying, increasing and decreasing. You know what is exponential, e to the power minus. So with a single component and constant height. You do not vary the height. So height is fixed, say 300 kilometer, and your atmosphere is exponentially varying. That means to the top also it is decreasing, and at the bottom also it is decreasing. So you have a kind of a maximum density somewhere at the middle. So that explains actually. So he tried to explain the observation. So if you cannot have a maximum density area somewhere, then you cannot explain the reflection. Basic theory of radio propagation. It is just what is called total internal reflection. So for total internal reflection, you need to have different density structures with a maximum from where your maximum, or in this case, of course, density is inversely proportional to refractive index. So somehow you should have a layer, varying density layer with a maximum somewhere from where the radio wave will come back. Theory was known. Propagation of radio waves was well known. So you need to have a layer somewhere over the Earth where the ionization will be maximum and your refractive index will be minimum, so that you get a what is called total internal reflection. Total internal reflection. If you send it vertically, it will be total internally reflected, come back to Earth. Otherwise, it cannot. So, plain horizontal stratification. Stratification means it is layered and plain and horizontal. The layers are horizontal, not vertical. You do not have vertical layers. You assume that the atmosphere is layered horizontally. Okay, that is what is true. We have the D layer, we have the E layer, we have F1 or F2 or say F. All are horizontal layers. All are horizontal layers. You do not have a vertical layer. Okay, so this is also true. Now, absorption of solar radiation is proportional to the number density of gas particles. That means the solar radiation which is received and absorbed will be proportional to the number density of gas particles. More the number of gas particles, more will be the radiation absorbed. Similarly, the constant absorption coefficient, that is monochromatic radiation, and the single absorption. He also assumed, because of to simplify the process, he assumed that it is a monochromatic radiation, and monochromatic means single frequency, and a single absorbing component. You have a kind of a, say, if it is O, not O2 or N2, then it is a single absorbing component. Only O is absorbing. Only O is the absorbing atom or molecule, and it absorbs. Okay?
Sir,
Yeah.
I think
Time is up.
mute কৰি দিয়াচোন হেৰি মিউট কৰি দিয়া এইটো চিষ্টেম মিউট কৰি দিয়া
Yes, yes.
তাৰমানে হেৰি নহয় 10:30 হ'ল যে নেক্সট ক্লাছ থাকিব
Yes, yes.
এইখিনিতো কাইণ্ডলি ষ্টাৰ্ট কৰি